I am Meenakshi, Chemistry Honors final year from Pandit Nikyam Sharma Government College, Rohtak. Today our chapter is hard and soft acids and bases. The term acid and bases are routinely used in our daily life. The chemists have been classifying substances as acids and bases since a long time. Lavoisier noted that the common element in all acids was oxygen. The word oxygen in Greek means acid former. However, Humphrey Davy showed later that all acids contain hydrogen. It was in 1884 Arrhenius, a Swedish chemist, developed the theory of acids and bases, known today popularly as Arrhenius theory of acids and bases. According to Arrhenius, an acid is a substance which gives hydrogen ions in aqueous solution, and base is a substance which gives hydroxyl ion in aqueous solution. The strength of an acid or a base depends upon the capacity to provide H positive and OH negative ions respectively. The process of neutralization of an acid by base can be represented by the reaction H positive plus OH negative gives H2O. In 1923, J. N. Bronsted and T. M. Lowry independently proposed a new acid-base theory. According to their theory, an acid is a proton donor, whereas a base is a proton acceptor. The acid-base reaction is regarded as a proton transfer reaction. In 1923, G. N. Lewis gave another general definition of acid-base behavior in the terms of electron pair donation and acceptance. However, this theory got the recognition in 1938. According to the Lewis, an acid is a substance which can accept a pair of electrons, while a base is a substance which can donate a pair of electrons. In other words, an acid is an electron pair acceptor, while base is an electron pair donor. The earlier definition of the acids and bases were solely based upon the observable properties such as taste, ability to dissolve substances insoluble in water, and their effect on vegetable dyes. The term acid was applied to substances that have sharp or sour taste, turns blue litmus red, react with certain metals to liberate hydrogen gas, and have ability to dissolve substances insoluble in water. On the other hand, the term base was applied to the substances that have a bitter taste. Soapy feel turns red litmus blue. However, the tasting and feeling chemicals are dangerous method of determining whether the substance is an acid or a base. You should never ever taste or touch the solutions of chemical in laboratory. There are, however, other methods of recognizing acids and bases. For example, acids and bases change the color of certain dyes, popularly known as indicators. One of the most common indicators in vegetable dye obtained from the lichen is known as litmus. Aqueous solution of acid turns litmus red, whereas aqueous solution of bases turns it blue. Thus, any substances which has an unshared pair of electrons can act as a Lewis base, whereas a substance which has an empty orbital to accommodate a pair of electrons act as a Lewis acid. In other words, substances capable of donating a pair of electrons are regarded as Lewis base, and the substances capable of accepting the pair of electrons are regarded as Lewis acid. The acid base or neutralization reaction may thus be regarded as donor acceptor reaction or coordinate covalent bond formation reaction. The classical example of Lewis acid base reaction is that of between boron trifluoride and ammonia. Using electron dot diagram, we can see the boron trifluoride in the Lewis is a Lewis acid and ammonia is a Lewis base, shown in the reaction where ammonia donates a lone pair of electron to BF3 and forms a coordinate bond between both of them. Lewis' concept of acid and bases is very commonly used because of its simplicity and the ease with which the formation of coordination compound can be explained. In brief, all usual ligands can be regarded as Lewis base, whereas all metal ion can be regarded as Lewis acid. The degree of affinity of metal ion for the ligands can be termed as Lewis acidity, and the tendency of a ligand to combine with the metal ion can be regarded as Lewis basicity. Hard and soft acids and bases. An acid-base reaction, according to the Lewis concept, involves the reaction between donor and acceptor as to form a complex as given below. A plus B is the donor here, gives the complex AB having the coordinate bond between them. The formation of a stable complex between the donor B and acceptor A depends upon the nature of the species A and B involved. It has been known since long that the certain ligands form more stable complexes with the metal ions such as Ag positive, Ag2 positive, Pd2 positive, Pt2 positive. On the other hand, certain ligands form stable complexes with metal ions such as aluminium 3 positive, cobalt 3 positive, platinum 4 positive. Based upon the preferential bonding, the acids and bases have been classified into two groups, that is class A and class B according to their preferences. Class A metal ion include alkali metal, alkaline earth metal, lighter and more highly charged ions like titanium 4 positive, chromium 3 positive, aluminium 3 positive, iron 3 positive, cobalt 3 positive, etc. and hydrogen ions. Class B metal ion include heavier transition metals of second and third transition series, that is cadmium 2 positive, mercury 2 positive, palladium 2 positive, platinum 2 positive. Heavier transition metals in lower oxidation state, Ag positive, Hg2 positive, copper plus 1 charge. Low valent metal ions such as zero valent metal in metal carbonyls. Depending upon the type of metal ions, ligand can also be classified as class A or class B depending upon their preferences. Class A ligands include molecules or ions with donor atom like nitrogen, oxygen, fluorine, chlorine, etc. And it is important to note that the class A ligands prefer to form a strong complex with the class A metal. Class B ligand include molecules and ions with donor atoms phosphorus, arsenic, sulfur, selenium, iodine, etc. Class B ligands prefer to form complexes with class B metal ions. It was in 1963 Pearson coined the term hard and soft acids and bases for class A and class B metal ions and ligands respectively. Accordingly, class A metal ions are referred to hard acid while class B metal ions are called soft acid. Similarly, class A ligands are named as hard bases whereas class B ligands are termed as soft bases. In summary, according to Pearson, class A acids are hard acids like hydrogen, lithium, plus 1 charge, Na, plus 1 Be, plus 2 Mg, plus 2 chromium, plus 3 iron, plus 3. Class B acids are soft acid, Ag plus 1, Pd plus 2, copper plus 1, Pt plus 2, etc. Class A bases are hard bases H2O, NH3, fluorine negative, ROH, etc. Class B bases are soft bases like R3P, R3AS, R2S, iodine, SCN negative, etc. Classification of acids and bases is hard and soft. Pearson observed that it is possible to correlate acid-bases interaction on the basis of hard and soft acids and bases. He observed that the type A metal ions that acids were small, compact, and not very polarizable. And these preferred ligands bases that are also small and less polarizable. He called these acids and bases as hard. On the other hand, the type B metal ions and ligands they prefer appears to be larger in size and more polarizable. He described these acids and bases as soft. Pearson generalized the acid-base relationship and expressed hard acids prefer hard bases and soft acids prefer soft bases. Classification of acids. Hard acids are cations of smaller size. Hard acids are cations of higher oxidation state like chlorine 3 positive, 7 positive, 5 iodine 5 positive, iodine 7 positive. Hard acids are molecules or cations with lesser number of valence electron. Hard acids holds the valence electron tightly and consequently are not easily polarizable. In summary, hard acid binds strongly to a proton. Hard acids are small sized, compact, and are not easily polarized. Look at table 4.1 also reveals that the soft acids possess the following characteristics. Soft acids are the cations of larger size or heavier elements. Soft acids are the cations of lower charge. Soft acids are the molecules or ions with larger number of valence electrons. Soft acids do not have the valence electron tightly and are therefore easily polarizable. In summary, soft acids are the large-sized and easily polarizable ions or molecules that bind strongly to highly polarizable ion or molecule. It is important to note that there is no sharp division between the hard and soft acid. There are a number of lace acids that are neither too hard nor too soft acids. Such type of acids that are neither too hard nor soft are called borderline acids, which are shown on the extreme right of table 4.1. Borderline acids have properties which are intermediate between the hard acid and hard bases. In case of borderline acids, the properties such as size, oxidation state, and polarizability of cation molecules are neither too low nor too high. On the other hand, soft acids will show the opposite trend and the following order of preference for the binding donor atom or ion with the group is observed. Like I negative is greater than Br negative, greater than Cl negative, greater than F negative. What type of interaction do you expect between the hard acid and hard base? Since both hard and acids and hard bases are not easily polarizable, their interaction are predominantly ionic. What type of interaction do you expect between the soft acid and soft base? Since both the soft acids and soft base are usually polarizable, the interaction between them are predominantly covalent. Classification of bases. A general classification of some commonly used ligands into hard and soft bases along with their borderline bases are represented in the table. A glance of the table 4.2 reveals some of the important characteristics of hard bases. Hard bases bind strongly to the proton. Hard bases contain donor atom of high electronegativity. The donor atom in hard bases possesses low polarizability. The hard bases are not easily oxidizable. Hard bases contain empty orbitals of high energy. In summary, hard bases bind strongly to a proton. The donor atom in case of hard bases is of high electronegativity and low polarizability. Further inspection of table reveals that the following feature observed in case of soft bases. Soft bases contain donor atom of low electronegativity. Soft bases contain donor atom of high polarizability. Soft bases get easily oxidized. Soft bases are associated with empty low-lying energy orbitals. In brief, soft bases contain less electronegative nonmetals. The donor atoms in such bases possess donor atoms that are easily polarized. Just as there are borderline acids, there are borderline bases also. The properties of borderline bases are in between those of soft and hard bases. It is important to note that the categories are not rigidly divided. For example, the halide ion from the very hard fluoride ion through the hard borderline chloride ion to the borderline bromide ion and soft iodide ion. Soft acids, also known as class B metal ions, are the group of metal ions that are in the low right portion of the metallic element shown in the table. Pearson HSAB principle. Pearson proposed a simple rule for predicting the stability of coordination compound formed between the acid and base. This rule is quite often named as HSAB principle. According to the Pearson HSAB principle, hard acids prefer to bind with hard bases, soft acids prefer to bind with soft bases. It is important to note that the hardness and softness of acid and base refer only to the hard and soft interactions. It is not by no means related to the strength of acids and bases. For example, both F negative and OH negative ion are hard bases, but the basic strength of OH negative ion is 10 raised to power 13 times that of fluoride ion. In other words, hard acid will show the following order of preference of binding the donor atoms or ions with the group. जैसे fluorine is greater than chlorine, then bromine, then iodine. Application of HSAB principle. Applications of HSAB principle. Pearson principle of HSAB has number of applications in non-organic chemistry. Some of these are discussed below. Stability of complexes. We have already noted the hardness and softness of acids and bases are related only to the hard and soft interaction. Hardness and softness of acids and base has nothing to do with the inherent acidic or basic strength of acids or bases. For example, both OH negative and F negative ion are hard bases, although OH negative ion is a stronger base than the fluoride ion. In fact, OH negative ion is 10 raised to power 13 times more stronger than base than fluoride ion. However, in HSAB principle, both OH and fluoride ions are at par with each other. Pearson in 1963 explained the relative stability of the coordination complexes on the basis of HSAB principle. Let us consider the example of general reaction between the Lewis acid and Lewis bases. Lewis acid A and Lewis base B complex form AB. The complex AB will be more stable if A and B are either both hard or both soft. The complex AB will be least stable if A is hard, B is soft, or A is soft or B is hard. Example of a complex between the soft acid Ag positive and soft base I negative is quite stable in contrast to the between a soft acid Ag positive and hard base F negative. Similarly, the reaction between the lithium iodide and cesium fluoride resulting in the formation of lithium fluoride and cesium iodide constitute an interesting example suggesting the preferential stability of soft and hard combinations. Some other examples of reactions suggesting the stability of soft and hard interaction is given below. CuI2 plus CuF gives CuF2 having hard interaction plus 2Cui having soft interaction. The rule of thumb in determining the stability of complex is preferential formation of hard and soft interaction. Why COF63 negative complex is more stable than COI63 negative? In both the complexes COF63 negative and COI63 negative, the oxidation state of cobalt is +3. Cobalt 3 positive is a hard acid, therefore its combination with a hard base that is F negative will lead to COF63 negative, which is a hard interaction. On the other hand, the combination of CO3 positive with a soft base I negative will lead to a COI63 negative, which is a hard soft interaction. Thus, F63 negative is more stable than CuI63 negative. It has also been noted that the combination of hard or soft ligands with metal ion is always preferred over combination of a mixture of hard and soft ligands with a metal ion. For example, the complexes COCN5I3 negative and CONH3F2 negative are far more stable, whereas the complexes COCN5F3 negative and CONH3 5I3 positive are unstable. This is because Cn negative and I negative are both soft bases, whereas NH3 and F negative are both hard bases. Classification of acids and base. The acids and base can be classified as hard or soft depending upon their preference for hard and soft reactant. Let us consider the following reaction: BH positive plus CH3H positive gives CH3HTP positive plus HT plus H positive. We already know that the H positive is a hard acid, whereas CH3HT positive is a soft acid. If B happen to a hard base like NH3, the reaction on left hand side will be preferred, like NH4 positive plus CH3HT positive are present on the left side, and on the right side CH3HT positive NH3 plus H positive. Conceptually, ammonia can be written as NH4 positive, that is equal to NH3 plus H, hard interaction, hard base, hard acid, which means the formation of NH4 positive ion is preferred because of hard acid H positive and hard base NH3 interaction. On the other hand, if B is soft base like R2S, and the right hand side reaction will be favored as shown. R2SH positive plus CH3HG positive gives CH3HGSR2 plus H positive. Conceptually, CH3's HGSR2 positive can be written as CH3HG positive plus RSR2, soft acid and soft base, having soft interaction, which means the formation of CH3HGSR2 is preferred because of soft acid and soft base interaction. Similarly, acid A can be classified as hard or soft depending upon the direction of equilibrium. AF plus SCN gives ASCN plus F negative. We know F negative is a hard base and SCN is a soft base. If A is a soft acid like Ag positive, then the above reaction in the forward direction is favored. AgF plus SCN, soft hard plus soft, gives AgSCN soft plus F negative hard. Conceptually, AgSCN is formed through soft interaction. Hence, according to HSAB theory, the reaction is preferred in forward direction. On the other hand, if A happens to be hard acid, then the forward reaction is not favored, rather the backward direction is preferred. NaF plus SCN are given by NaSCN plus F negative on the left side. Conceptually, NaF is formed through hard interaction. Thus, according to HSAB theory, the reaction is preferred in the backward direction. OH negative is much stronger base than SO32 negative and hence cannot be displaced by a weak base SO32 negative. This reaction, however, is favored by HSAB principle. CH3CdOH soft plus SO32 negative soft gives CH3CdSO3 negative plus OH negative. It is important to conclude at this stage the Lewis acid and Lewis base reaction are governed by two independent principles, that is the strength of acids or base, softness and hardness of acids or base. The definition of hardness primarily used the idea of polarizability, which states that less polarizable species is hard and more easily polarized is soft. For ions of similar charges, the ratio of charge to radius should be used to assess the relative polarizability. However, HSAB principle does not take into consideration the quantitative idea of relative hardness and softness of species. In summary, the major limitation of HSAB principle are: HSAB principle is too general and without any qualitative scale of measurement. HSAB principle does not take into consideration the acidic and basic character of the compounds. HSAB principle fails to explain the feasibility of the reaction CH3 positive gaseous plus H2 gaseous gives CH4 gaseous plus H positive gaseous in spite of soft interaction. Limitations of HSAB principle. The hardness and softness of an acid or a base is primarily related to stability of hard and soft interaction. There has no concern with the acidity or basicity of acid or base. For example, OH negative and fluoride ion are well known hard bases. However, the basicity of hydroxide ion is very large as compared to the fluoride ion. In fact, the basicity of hydroxide ion is 10 raised to power 13 times than the fluoride ion. In fact, a strong acid is well known to replace a weak acid. For example, the reaction between the sulfite ion and hydrogen fluoride proceed in the forward direction. It means that the stronger base SO3 negative can easily displace the weak base F negative ion from the acidic hydrogen fluoride. However, the above reaction is not favored according to HSAB principle as detailed below. SO3 negative plus HF gives HSO3 negative and F negative, which only favors hard and soft interaction. Similarly, a very strong base OH negative can displace a weak base from soft acid methyl mercury to cation. OH negative plus CH3HTSO3 negative gives CH3HGOH plus SO3 negative. However, the above reaction is not favored according to HSAB principle, which only favors hard or soft interaction. In both the above cases, it is the inherent strength of bases that forces the reaction in forward direction in spite of less preferred formation of soft hard and hard soft pair in the product. This is true in case especially when the inherent strength of bases being compared are significantly different, the order of basic strength being OH negative greater than SO3 negative greater than F negative. In other words, significant different basic strength forces the reaction against the wish of hard soft reaction interactions. However, when both the strength of acids and base and hardness and softness are not significantly different, then the HSAB principle works very well, resulting in the products having hard and soft combination. Symbiosis. The hardness or softness of an acid or basic center. Acidic or basic center is not an inherent property of an atom but depends upon the substituents. Thus, ammonia is a hard base while pyridine is a borderline base. The acidic B3 positive ion is a borderline between hard and soft acid. The addition of three small size non-polarizable F negative ions makes it a hard Lewis acid BF3, whereas the addition of electron donors and easily polarizable group like hydride ion make it a soft Lewis acid. The difference in the hardness and softness of BF3 and BH3 can be illustrated nicely in the following example. R2S BF3 plus R2O gives R2 BF3 plus R2S having hard interaction. R2O BH3 hard soft plus R2S soft, R2S BH3 soft plus R2O. Jorgensen observed the hard ligands have tendency to combine with metal ion having hard ligand, and soft ligand have the tendency to combine with the metal ion already having the soft ligands. He coined the term symbiosis for such interaction. The hard BF3 molecules prefer to combine with the hard base F negative to form tetrafluoroborate BF4 negative, whereas soft acid BH3 prefer to combine with soft base H negative ion to give tetrahydroborate BH4 ion. An important outcome of symbiosis is that symmetrically substituted compounds are formed in preference to the unsymmetrically substituted compounds. For example, compounds containing mixed substituents interact strongly to the yield symmetrical compounds with the same substituent as given below. BH3F negative plus BF3H positive H negative gives BH4 negative plus BF4 negative. In brief, symbiosis may be defined as the tendency of a soft acid to combine with a metal ion already having soft ligands and the tendency of a hard ligand to combine with a metal ion already having hard ligands. Theoretical basis of hardness and softness HSAB principle. Electrostatic interaction theory. According to this theory, the hard acid and hard bases form purely ionic compounds. Therefore, the hard interactions are purely ionic or electrostatic. Most of the hard acids such as lithium, Na positive, K positive, and hard bases such as O2 negative, F negative, OH negative as well known to form ionic compounds. We know that the electrostatic energy of an ion pair is inversely proportional to the interatomic distance. It means the smaller the ions, smaller will be the internuclear distance, and hence greater will be the electrostatic energy between the ions. As a result, the final compound formed by hard acid and the hard base will be highly stable, polarizing power and polarizability. Electrostatic interaction cannot explain the soft interaction because of the bigger size of soft ions. Therefore, the interaction between the large size acids and bases must involve covalent character. For example, soft acids such as Ag positive, Hg positive, Cu positive, etc. form strong compounds with strong bases like S2 negative, I negative, etc., which have substantial covalent character. Almost all soft acids have 6 and more d electrons. Soft acids with D10 configuration are excellent soft acids like Ag positive, Hg2 positive. It is these d electrons that have more polarizing power. Secondly, the soft bases like S2 negative and I negative are easily polarizable. Thus, bonding between the soft acid and soft base is largely covalent. Natural occurrence of ores and minerals. The natural occurrence of ores of certain metal can be easily explained on the basis of HSAB principle. Hard acid metal ions such as magnesium, calcium 2 positive, aluminum 3 positive, iron and chromium 3 positive frequently occurs as their oxide, fluoride, chloride or carbonate. This is primarily due to the preferred hard acid and hard base interaction. We know that the oxides, halides, and carbonates are so hard bases. These hard acid metal ions cannot occur in sulfides, and S2 negative is a soft base and cannot form stable compound. On the other hand, soft metal ions such as copper plus 1, Ag plus 1, Cd plus 2, Hg plus 2, Pd plus 2 occur invariably in ores as they are sulfide due to soft acid base interaction that result in the formation of stable complex. Interestingly, the borderline acid like CO2 positive, Ni2 positive, Pb2 positive, Zinc2 positive can occur both as sulfide as well as their oxides or carbonates as a result of their intermediate character. Catalytic poisoning. All metal atoms are soft acids. Some of the metals, namely vanadium, chromium, nickel, palladium, platinum, are well known catalysts. These metal catalysts have been found to be easily poisoned by the soft bases like carbon monoxide, unsaturated hydrocarbon, and organophosphine and organoarsine compounds, etc. This poisoning is attributed to the soft acid soft base interaction between the metal atoms and the soft ligands. In fact, the soft ligands are absorbed strongly on the surface of metal and block the reactive sites by forming metal complexes. In other words, the metal atoms lose their activity and are said to be poisoned. Thus, the soft bases complex with metal in the atomic state will act as poisonous toward the metal catalyst. Electronegativity and hardness softness. The hardness and softness are related to electronegativity. Species with higher electronegativity values are assigned greater hardness, and are those with lower electronegativity values are assigned greater softness. Electronegativity conventionally means the power of an atom in a molecule to attract electron toward itself. However, in this case, it refers to the power of an individual ion participating in the reaction. For example, lithium atom is known as highly electropositive metal, but the cationic species lithium plus 1 has a greater tendency to attract the electron toward itself. As a result, lithium plus 1 is considered to be more electronegative and hence it is a hard acid. On the other hand, heavier transition metals ion in the low oxidation state like Cu plus 1, Ag plus 1, Hg plus 1, Cd plus 1 have relatively low ionization potential and consequently possess low value of electronegativity. As a result of these ions are considered as soft acids. Using the same concept of electronegativity, we can define the hard and soft bases. This relationship between hardness and electronegativity can explain several important features as to why CF3 is harder as compared to CH3. BF3 is harder as compared to BH3. Ammonia is harder than CH3 thrice, and BF3 is harder than phosphine, which in turn is harder than CH3 thrice P trimethyl phosphine. Mulik and Jaffe define the electronegativity as a linear function of partial charge developed on an atom according as electronegativity is equal to A plus B delta naught. A is the electronegativity of atom and delta naught is the rate of change of electronegativity with charge. The electronegativity value of A of the atom is similar to the following in Rocho, and the parameter B is called charge coefficient. Small, hard, and non-polarizable atoms have higher value of B, whereas the large, soft, and polarizable atoms have small value of B. Parr and Pearson introduced a new term called absolute hardness for neutral as well as charged species and correlate it with absolute electronegativity. The absolute hardness is defined as the half of the difference between the ionization energy and electron affinity. N is equals to I minus A upon 2. I is ionization energy, A is electron affinity. We know that the Mulliken definition of electronegativity so, is X is equals to I plus A plus 2. The hardness of a base B and acid A may be given as NB is equals to 1 by 2 I B positive minus A B positive. Na is equals to 1 by 2 Ia minus Aa. In order to understand as to why the equation the base is represented as B positive, whereas in equation number 4.7 acid A is represented as such A, let us consider the interaction of an acid and base to form a compound AB as A acid B base gives compound AB having partial positive and partial negative charge. In the formation of a compound, a AB electron will move to BA, which is indicated by partial positive charge and partial negative charges. Hardness of B refers to a species going from delta plus to charge plus 1 plus delta naught on ionization, while hardness of A refers to a species in ionization from delta minus to charge 1 plus delta minus. If the shift of a charge is taken as equal to 0.5, then the charges on B becomes 1.05 plus is equals to 1.5. Absorbance 1 plus minus 0.5 gives 0.5. Thus the charge on the B changes from 0.5 to 1.5. Thus the charge on B changes from 0.5 to 1.5 with the average 1, and a charge that on A changes from minus 0.5 to 0.5 with average 0. This justifies the reason why species B is shown as B plus. A close inspection of the table reveals the absolute hardness value is in good agreement with their known chemical behavior. Hydrogen is the only exception which is different in all the three tables. It is advisable to consider it as a special case. With the exception of H negative, the values of hardness parameter of all other bases are as expected. The hard bases F negative and OH negative have larger values of Nb, while soft bases S and SCH3 negative have smaller values. The hard acids such as Na positive, Mg2 positive, Al3 positive have larger Na values, whereas the soft acids such as Ag positive, Cu positive, Au positive has small Na values. The borderline metal ions such as Mn2 positive, Fe2 positive, and I plus 2, Cu plus 2, Zn plus 2 have intermediate values. It is interesting to note that down the column in a periodic table from magnesium to barium plus 2, there is a steady increase in the softness. Similarly, the observation of softness is made in going from nickel plus 2 to palladium plus 2. There is also an expected increase in hardness value with increase in the oxidation state as Fe0 3.3 3.87, Fe plus 2 7.30, Fe plus 3 13.10. The Ne values of Tl plus 3 suggest it to be harder acid, where Tl plus 3 is well known to be chemically softer. Soft acids are generally Transition metals in low oxidation state contain loosely held d electrons. These electrons can be easily donated to ligands. On the other hand, soft bases are pi bond acceptors such as CO, phosphines, alkenes, alkynes. In soft acid-base interaction, pi bonding is very important. Sigma bond formation due to the donation of electron from the base to the metal is reinforced by the pi back bonding from metal to base. Relation to molecular orbital theory, the MOT is a powerful tool for explaining structure and bonding, visible UV spectra, and detailed mechanism of chemical reaction. The concept of absolute electronegativity hardness can also be explained using MOT. The ionization energy is the measure of energy of highest occupied molecular orbital HOMO, whereas electron affinity is the measure of the energy of LUMO. According to Hoffman's theory, E HOMO is equals to minus I, E LUMO is equals to minus E. Hardness and softness depend upon the average gap between the HOMO and LUMO. The combination of soft acid with soft base is analogous to the situation in which LUMO of Lewis acid has about same energy as HOMO of Lewis base. The combination of orbitals result in greatly reduced energy of electron pair coming from the base, thus giving a strong covalent bond. For the hard acids and hard bases, there is a great mismatch of LUMO and HOMO energies, so that there is a little energy advantage to be gained from orbital interaction. Thus, the covalent bonding will not occur to any significant extent, and in ionic interaction will result instead. Thank you.